Hello everyone, in this video we're going to be talking about how to actually be solving differential equations. Solving differential equations. And to solve a differential equation, okay, we're going to use, to solve some differential equations, okay, I should rephrase that, because many differential equations cannot be solved in the technique we're about to do today, okay? We're about to do in this video, okay? You can easily make a differential equation that either is very difficult to solve and can't be solved with this technique, or just impossible to solve. I'm not saying like very difficult as well. I mean, you can't find a solution. Okay, you have to resort to an approximation. But we're going to learn about solving a separate category of differential equations known as separable differential equations. And the reason why we call them separable differential equations is because we use this technique called separation of variables, which is a lot easier to explain when we actually do an example, okay? So this will probably be a long video since there are so many quirks to separation of variables, but let's get started. So let's consider the equation dy dx equals x over y. Dy dx equals x over y. So what do you do? Okay, what do you do? Now, in order to actually solve this, first, what we're going to do, and I'll explain why we do this a bit later, okay, in a minute, we're going to multiply each side by dx. Okay, so when we use separation of variables, we treat the derivative as if it's a fraction. Okay, we treat the derivative as if it's a fraction. So we can multiply by the denominator of dy dx. So we have dy equals x over y dx. And now we multiply by y on both sides. So we get y dy equals x dx. And now is why we call it separation of variables. Okay, you can start to see that. You have all y's here and all x's here. Okay, so to use separation of variables, you have to be able to get all the y's on one side and all the x's on the other. So the dy's and the y's must be on the side of their own, and any other y's that might be there, as well as the dx's and the x, okay, should be on the other side. And the reason why we do this is it allows us to use integration. You can integrate both sides with respect to the variable. Okay, so on the left, we integrate with respect to y, so our variable is y, and on the right, we do an integration with the variables x. Okay, so the reason why we do separation of variables is that this integration can take place, and we can get rid of the dy's and the dx's. Because remember, integration is a reverse of differentiation. Okay, so to get rid of this differential dy and dx, okay, to get rid of dy and dx, we have to do integration. So we have y squared over 2, so we just integrate, equals x squared over 2 plus c. Call it c1 because there's also a c2 over here. So now we want to solve for y. So we subtract c2. So y is redundant to write two constants. Okay, only one on one side. Because c1 minus c2, because they're arbitrary constant, we can simply replace by a big old c right over here. Okay, the subtraction of two arbitrary constants is another arbitrary constant. Okay, so you have y squared over 2 equals x squared over 2 plus c. Now, if you multiply by 2, we get y squared equals x squared plus 2c. Okay, and 2c equals some other constant. Okay, we'll call c 0. Okay, this is why I usually don't do an operation, apply the operation to c, since that'll usually result in yet another constant. Okay, and now you can take the square root. Y equals the square root of x squared plus c 0. Okay, or just a c, a constant of integration. This is a general solution. Okay, this is a general solution. So if you were to have a constant, put any constant in here, it would satisfy the differential equation. Okay, it would satisfy it. Now, what if we actually had a solution point? Okay, so let's look at this equation. Let's look at the equation dr ds equals e to the r minus 2s. Okay, and we're given the initial condition that r of 0 equals 0. Now, this is actually not that hard, okay? Because if you remember exponent properties, now it becomes really not that hard, okay? Because what we can do is rewrite the differential equation as dr ds equals e to the r over e to the 2s. So you're just utilizing the exponent properties. So we're going to multiply by ds. So you have dr equals e to the r over e to the 2s ds. And we're going to divide by e to the r. So we have dr over e to the r equals ds over e to the 2s. And now we're going to integrate. 1 over e to the r, dr equals 1 over the integral 1 over e to the 2s ds, which is simply the integral of e to the negative r dr times e to the negative 2s ds. And now it's a lot easier to integrate, right? So we have negative e to the negative r, and because of last time, we don't need to add a constant on this side. We literally need a constant on this side, and that will be fine, okay? So we integrate this, and you can mentally integrate it if you want. Negative 1/2 e to the negative 2s plus c, okay? And here is where that constant comes in, okay? Here's where our constant comes in. So if r of 0 equals 0, that means our initial point is 0, 0. Okay? So let's call this r, s. They're both the same. So we would substitute in 0 in for r and another 0 in for s and solve for c. So you have negative e to the negative r. So negative e to 0, which is negative 1, equals negative 1/2 times 1 plus c. And you get c equals positive 1/2. Sorry, negative 1/2. Okay, so c equals negative 1/2. Okay. Now c equals negative 1/2. You could plug this in back over here. Negative e to the negative r was negative 1/2 e to the negative 2s minus 1/2. So if we want to get r of s, okay, if you want to get r of s, should be s comma r then. Should be s comma r if r's are in function. Okay, but it doesn't really matter. Okay, it doesn't matter the constant. Okay, it doesn't matter the value of the constant. Since 0, 0, you have two values that are the same. Okay, so we want to solve for r. Okay, we want to solve for r as a function of s, since we're given that r is a function of s right in our definition. Okay, so what would you do? Well, we'll take the negative. Okay, we would multiply by -1, so we have e to the negative r equals 1/2 e to the negative 2s plus 1/2. Okay, so it's basically 1/2. We can factor out 1/2 e to the negative 2s plus 1. Okay, and now what we're going to do is take the ln. ln of both sides. So if we take ln of both sides, we're basically solving for r at this point. Okay, ln of both sides is equal to the ln of 1/2 e to the negative 2s plus 1. So we have negative r, and to get rid of this negative sign, we can just multiply by -1, and we get the negative ln of 1/2 times e to the negative 2s plus 1. This over here is our particular solution, since there are no constants here. We use this to solve for c. Okay, and using our value for c, we were able to come up with this expression for r, okay, in terms of s, and s alone. So there are many applied problems that you can do with differential equations, okay? And many of them have to do with heat. Okay, so here's a good one involving heat. Okay, and you would do this. Okay, you would solve this equation using separation of variables. Okay, so here is a good application. Okay, so let's say an object. Okay, an object. Okay, an object is removed from a furnace or an oven. Okay, and initially it starts off at 1,500 degrees Fahrenheit. Okay, 1,500 degrees Fahrenheit. Okay, and it's placed into an environment of 80 degrees Fahrenheit. Okay, and after 1 hour, the temperature is 1,120 degrees Fahrenheit. Okay, so, and the object cools down at a rate of dt, okay, d capital T with respect to t, the derivative of temperature with respect to time, equals k times y. Okay, so let's not put y, let's put t, minus 80. K times y minus 80. Right, k times t minus 80. Okay. Where k is a constant, where k is our constant. Okay, so we want to find out the temperature after 5 hours. Okay, we want to find the temperature after 5 hours. Now, what do you do? Okay, what we can do is solve the differential equation. Okay, solve the differential equation in terms of t. Okay, since we're given, we want to find t of t. So you would do separation of variables, okay? And you would separate this quantity, so I have dt over capital T minus 80 equals k times d lowercase t. And now you would be able to integrate d capital T over capital T minus 80 equals integral k times dt. And now that gets us ln of t minus 80, okay, equals kt plus c, where c's are constant. So now you have two constants, okay? You have two constants. So what we're going to do is we're going to have to solve for big T and then look at the constants at that point. Okay, so what we're going to do is take e to these quantities. So you have t minus 80 equals e to the kt plus c. Now this equals e to the kt times e to the c. And we're going to define another constant, b, that equals e to the c. And now, just like that, if you add 80 to both sides, you have 80 plus b times e to the kt. Now, how does this help us? How does this help us? Now, we know at time t equals 0, we start off at 1,500 degrees. Okay? So at time t equals 0, that gets rid of the k factor. Okay? So t of 0 equals 80 plus b times 1, since t is 0. And t of 0 we know is 1,500 equals 80 plus b. So b has to equal 1,420. Okay? Yes, I did right. So now we can substitute in for b. So our current model is t of t equals 80 plus 1,420 e to the kt. Okay, e to the kt. Now what's k? Well, they give you another amount. After 1 hour, the temperature is 1,120 degrees Fahrenheit. Okay? So let's delete some of this. Delete. So we have more space. Now, if t equals 1, okay, so we're measuring t in hours, then we have 1,120 equals 80 plus 1,420 e to the k. And now it's literally an equation that you have to solve for k. Okay? So you have 1,040 equals 1,420 e to the k. Or e to the k equals 1,040 over 1,420. Now we get to solve for k by taking the ln of both sides. And we get k equals ln of 1,040 over 1,420. And that is equal, you can take out a calculator and plug this in. Negative 0.3114. So now that we found both our missing constants using two pieces of information we have, we have our final model. T of lowercase t of lowercase t equals 80 plus 1,420 times e to the negative 0.3114t. And now if we plug in 5, need our calculator again, you get 80 plus 1,420 times e to the negative 0.3114 times 5. And that gets us 80 plus 1,420 times e to the negative 0.3114 times 5. That gets us a temperature of 379.29 degrees Fahrenheit. And that is the temperature. Just based on the equation that we get at the very beginning, that is the temperature the object will be in at t equals 5. And using separation of variables over here, and two initial conditions over here on the right, using our two conditions, t of 0 and t of 1, we were able to solve for both constants, the proportionality constant, and the constant of integration that was turned into this. Okay? And now you can see how powerful and how applicable separable differential equations are. You can apply them to real life by creating a differential equation, especially in science. You can create a differential equation to model very small changes in time and then make a model out of it, as we did right over here. Okay, this is our model that we created. And using this model, you can predict values and quantities that will happen at a particular time. Okay? So thanks for watching. If you have any questions or concerns, please comment. I will try to respond as quick as possible. Please like this video and subscribe, and make sure to pass it on to your friends if they need help as well. See you next time, and thanks for watching.